So thanks very much to the organizers for inviting me to this beautiful place and this beautiful conference. And today I'll talk about something maybe slightly unusual for me, because there's no string theory in this talk, but it's just about 3D gravity. And I want to explain a particular relation between 3D gravity and Teichmueller TQFT, which is some TQFT that I'll explain exactly what it is in the talk. And so this talk is based on work together in collaboration with Scott, who's in the audience here, and Meng Yang, who is an excellent student, grad student in Princeton. So, as we probably all know, there's a relation of 3D gravity and SL2R times SL2R Chern-Simons theory, and it has been discussed in an enormous amount of literature. So it started essentially with the work of Witten, and then there were many follow-up papers. So apologies if not all are cited here. And however, the relation between those two theories is sort of subtle and not particularly well understood. And the difficulty is, I think, the main difficulty is that both sides are not particularly well defined. So we neither know how to define 3D gravity properly, and we also don't know how to solve SL2R times SL2R Chern-Simons theory. And also, in particular, this hasn't been very useful so far, I would claim, for any work. So most works that treat 3D gravity somehow do their computation directly in the metric formalism and don't really use that relation very much. So it's more like a philosophical relation so far. And so for 3D gravity, we have sort of a patchwork of different approaches. I'll just talk about the bulk side here. I will not mention the boundary CFT. And I think none of them are particularly satisfactory. So some treat like various special cases and so on, but there's no overarching framework that can deal with all like arbitrary manifolds and so on. And similarly for the boundary CFT, we have a large number of different proposals, and most of them are somehow contradictory. So there's not a very clear picture of what should happen. So in this talk, we'll just sort of focus on formalism. So the goal will just be to describe 3D gravity in a better way. I won't say very much about holography or anything like that. And in particular, I want to replace that relation with SL2R Chern-Simons theory. I want to replace it with a sort of better defined TQFT and make it a more precise relation. So, and the TQFT that will appear is known in the literature as Teichmueller TQFT. And so sort of the subject started with a paper by Hermann Belinde, and then was treated in a series of papers by Jörg Teschner, and then sort of went off in the mathematical literature. So there are various papers by these mathematicians Kasheev and Anderson, and also by Mikhailov, sorry. So there's this TQFT, but it has a number of subtleties, and most of them are related somehow to the non-compact nature of the problem. And so there will be a continuous spectrum of Wilson lines and things like that, but most of them can actually be overcome. And so this gives you a framework that describes 3D gravity sort of in a useful way. And it's in particular computationally very useful. So I'll show you different computations that can be done. And so I think that's a useful framework to think about it. And in particular, this gives a prescription. So we'll propose an explicit prescription how to compute all 3D gravity partition functions on any hyperbolic manifold. So we cannot go all the way and take like any manifold that we want to, but at least all the hyperbolic manifolds, which are sort of most of the 3 manifolds we can do. And I should also say hyperbolic 3 manifold is just a fancy word of saying it's a 3 manifold that emits a classical solution to the classical equation of motion of gravity. So this talk has roughly 3 parts. And so first I'll explain the phase space of 3D gravity. This is all known stuff. There's nothing new here. And we go on and quantize the theory from there. And then I explain the relation to this Teichmueller TQFT and explain the precise dictionary that we propose. And then hopefully in this third part I can convince you that it's actually useful to do stuff. Okay, so let's start. So the classical story is that we can describe 3D gravity in the first order formalism. In the first order formalism, we have this dry bind here that describes symmetric degrees of freedom, and then we have the spin connection that describes the connection, and we can build these linear combinations and build 2 SL2R gauge fields out of them. And you can check that a mu plus and minus, they transform indeed like gauge fields under infinitesimal coordinate transformations and local Lorenz transformations. And you can also check that the Einstein-Hilbert action indeed gets mapped to the correct SL2R times SL2R Chern-Simons action, and you can compute the level. The level for the two theories is the same or opposite rather, and the level is related to the size of ADS measured in Planck units, or you can also write it in terms of the center charge of the boundary theory as computed by Brown and Henno. So there are two main issues with this. So the first one is on this slide, and it concerns invertibility. So in the gravity theory, there's an important constraint, namely the metric should be a positive definite object. We don't want negative length or zero length and things like that. So in particular, that means also that the dryband is invertible. However, in Chern-Simons theory, the gauge field can be whatever you want. There's no constraint whatsoever that like the sum of the gauge fields should be invertible or something like that. So this is the problem that we'll argue is completely resolved by going to this Teichmueller TQFT instead and not taking SL2R Chern-Simons theory. And this is sort of a win-win situation because this Teichmueller TQFT is much better understood than SL2R Chern-Simons theory. So this is the first problem. And the second problem are sort of global problems in these identifications. So in particular, if we're in gravity, we have to mod out by all the diffeomorphisms. So if we compute some gravity partition function, then we have to mod out by all the diffeomorphisms on our 3-manifold. And so these are in particular, there are these large diffeomorphisms. These are like the 3-dimensional analogs of the modular transformations that we know very well in 2D. And they're formalized in this mapping class group. So mapping class group is just the group of all the diffeomorphisms of some manifold, and you mod out by the group of diffeomorphisms that are small, meaning that they're continuously connected to the identity. And you get some discrete group, which is called this mapping class group. And in gravity in particular, we have to divide by this mapping class group. So like we also know this very well in string theory. In string theory, we have to divide out by the modular transformations once we compute the path integral. And here is exactly the same. So they're gauged in gravity, but on the TQFT side, it's very unnatural to gauge them, and they're actually not gauged. So if we are on the TQFT side, we will just not divide by these. And so this is not naturally resolved by going to this Teichmueller TQFT, because it's still a TQFT. It's not a gravity theory. But for hyperbolic manifolds, it turns out this mapping class group is always finite, and you can sort of deal by it by hand later on. So, and in general, I don't know how to deal with it. So these are the two main problems, and let's now discuss the phase space and see what the relation between this Teichmueller TQFT and gravity is. So it's useful to look at canonical quantization. So let's take some spatial manifold sigma. And if we're doing Chern-Simons theory, then the Chern-Simons phase space on sigma would be the modular space of flat SL2R times SL2R bundles on sigma. So this was luckily already partially explained by Ibu, because the flat means exactly that these connections that we start on our initial value surface should satisfy the Gauss law. So they should have zero curvature. So these are all the possible connections we can take as initial conditions, but most of them don't lead to good gravity solutions once we solve the equations of motion. So for example, we could put our curvature to be, our connection to be 0, which is not a very good gravity solution. However, if you look in the math literature, you see that this modular space of flat SL2R bundles, or if I'm more precise, PSL2R bundles on sigma is actually a disconnected space. So it's not a connected space, but there are different topological components, and they're labeled by a certain topological number. It's called the Euler number. And one of these components is called Teichmueller space. It's precisely the space that describes all the hyperbolic structures on the initial value surface. So, and now it's a non-trivial theorem that you can prove that if you start in this Teichmueller component, then precisely you get so both gauge fields need to be in the Teichmueller component, and you solve for the 3D metric, then you get precisely a regular metric. So, and that leads to the proposal that you can find in the literature, that the gravity phase space on the initial value surface sigma consists of 2 copies of Teichmueller space, which again is a subspace of what you would get in SL2R Chern-Simons theory, but it's a closed subset. Okay, so now we know what the classical story is. and we need to pass to the Hilbert space. And what do we need to do? So we need to quantize our phase space to get to our quantum theory. And so in particular, the Hilbert space of 3D gravity is essentially just obtained by quantizing 2 copies of Teichmueller space. And so this was already done in the literature, again started with the work of Velinde and Kashev and Teschner. And sort of the main takeaway result from this is that if you want to quantize Teichmueller space, then the wave function will be exactly a conformal block on the surface sigma. And the Hilbert space that you get from quantizing Teichmueller space is exactly the space of all Liouville conformal blocks, meaning that these are Virasoro conformal blocks with the additional condition that every state that appears as internal state has to be above threshold. So it has to be heavy and have conformal weight more than c minus 1 over 24. And these are precisely the conformal blocks that appear in Liouville theory. And so the Hilbert space of 3D gravity you can identify with just the space of Liouville conformal blocks, and you can sort of think of one factor as being left moving and the other factor as being right moving. Okay, so far this would not be extremely useful, because if we just have conformal blocks, we have some infinite dimensional Hilbert space, but just having some infinite dimensional Hilbert space is not very useful. We need more structure to do anything useful, and the additional structure that we usually have in 3D are these crossing transformations. So we can do on conformal blocks, we can do crossing transformations, and said in a fancy way, this defines your representation of the 2D mapping class group on your Hilbert space, because you can do large 2D diffeomorphisms on your initial value surface, and they need to map the Hilbert space back to itself, because it's still the same surface. And so you get some representation of the 2D mapping class group, which are just modular transformations. And just to tell you the most important sort of move in these crossing transformations is the usual thing that if you look at the full-point function, you can write the S-channel block in terms of T-channel blocks, and there will be some particular matrix in front here, which is called the Virasoro fusion kernel, and it relates to the T-channel blocks in terms of the S-channel blocks. And importantly, even though we don't know what the conformal blocks themselves are, we just know them in some kind of recursion relation sort of way, but we do know what this Virasoro fusion kernel is. It's some bunch of special functions of like upsilon types of function and so on. I didn't want to write it on this slide, but it's an explicit formula. And this is sort of the most complicated ingredient, and then there are also like simpler like braiding things and so on. But the point is that this representation is fully understood on this Hilbert space of conformal blocks. In particular, they also claim to satisfy the Moore-Seiberg consistency condition of rational conformal feed theory. Even though this is not sort of a rational conformal feed theory because everything is continuous, there are still like these consistency conditions. They're called the pentagon identity, hexagon identity, and these sort of things. And these Virasoro fusion kernels satisfy this, which basically means that this is a consistent representation of the 2D mapping class group. Okay, so this is what you get if you just quantize 3D gravity on the nose, basically. And as I said, this was all known in the literature. Yes, please.
You didn't tell me the representations on left and right, but there's a relation which shows them together, right? Because they're non-compact. Does that happen here or not?
So in principle, we have 2 independent representations on the left and the right.
And there's no relation?
No, so far not.
Are you just talking about compact spatial manifolds here?
Yes, let's say compact. I can allow punctures, but I don't want to put boundaries. We'll see how to put boundaries. Other questions?
That's the vacuum?
Yes, good. So, I mean, we are talking about the TQFT. So in the sense of the TQFT, everything is the vacuum, because everything has, there's no. Yeah, the vacuum block is not part of the Hilbert space. It's not normalizable. I didn't tell you what the inner product is. There's an explicit inner product on the space of conformal blocks. And if you compute the inner product of the vacuum block, it just diverges, as you would expect. It is there in 3D gravity, and it will actually make an important appearance. So maybe you'll ask again later. I mean, it's still in the Hilbert space. It's just not normalizable, but it's still part of the completion of the Hilbert space.
Sorry.
Yes.
Is there a simple characterization of this Teichmueller component from the point of view of the SL2R?
Yes, it has Euler number equal to 2 genus minus 2, equal to the Euler characteristic. That's the most simple characterization that I know.
Is there a natural operation that kind of restricts to this?
No, there is not, and that's kind of a mystery. Why there should be a consistent, so I mean, now we'll come to like defining a TQFT only based on the subspace. But there's no guarantee that if you do that, you will get something consistent. But it just happens that you get something consistent. Right, so that's what I wanted to say here. So from the point of view of gauge theory, we did some completely arbitrary thing. We took some phase space, we restricted ourselves to part of this phase space and quantized that and got some Hilbert space, which in principle is a part of the full Hilbert space that you would get in SL torch and Simons theory. And now what we want to do is to promote this to a full-fledged 3D TQFT. And of course, like Rajesh is saying, there's no guarantee that this will work. So usually if you do something like this, you get very bad things. But the fact that Liouville conformal blocks do transform nicely under crossing transformation, and that you can write an S-channel conformal block only in terms of T-channel conformal blocks, and you don't need anything else, means the whole system is closed under all these crossing transformations. And that's all the data that you need to define a consistent 3D TQFT. And this TQFT is known as the Teichmueller TQFT. Usually it's defined in a different way in the literature, but we're pretty sure that it's the same theory. So yeah, and sort of the catchphrase is that the relation of this TQFT to Liouville is exactly analogous to the relation of Chern-Simons theory with the compact gauge group and the WGW model. So the conformal blocks, so the states of this TQFT are the conformal blocks of Liouville, just as the states of Chern-Simons theory are the conformal block of WGW.
It isn't quite Liouville because you haven't imposed the constraint between left and right.
Well, but it is like the relation of Chern-Simons theory to WGW. The same is true there. So there the states in Chern-Simons theory are just holomorphic WGW blocks, but there's no mention of left and right movers. So I'm not claiming that they're equal or something. So this is a TQFT that satisfies all the usual axioms of TQFT, except for, importantly, one that was mentioned by Kristen. So it does not possess a trivial line. So there's not a line that does nothing, which is usually very important to have in like axiomatic formulations of TQFT. Or also put differently, there's the vacuum block is not normalizable. The vacuum block is not part of the Hilbert space. Or yeah, its norm is infinite. And so immediately if you like apply standard TQFT procedures, you'll run into serious trouble. So for example, you might want to compute the 3-sphere partition function. And the 3-sphere partition function usually you compute by some surgery procedure. And it turns out that it's the vacuum component of the modular S-matrix. But this is not well defined because the modular S-matrix, there's no vacuum block to start with, and it certainly doesn't map back to a vacuum block. So we don't know how to define this component here. And so that runs immediately into problems. And so more generally, if you perform surgery, that's what we usually do in Chern-Simons theory, then we get usually ill-defined expressions. That's sort of the difficulty that we were trying to understand. And one solution that we came up with is to consider Heegaard splittings. So that is a prescription or one way to compute consistently partition functions in this TQFT. And so Heegaard splitting is just a very simple thing. If you're given any 3 manifold, you can always write it as follows. You can write it as the union of 2 handle bodies. A handle body is literally, take like a Riemann surface and imagine this being filled. That's a handle body. And you take 2 of those and you identify them on the boundary. So you get some closed 3D manifold. But the catch here is that you might identify them with some non-trivial modular transformation before gluing them, which are represented by this phi. And yeah, and it's a little theorem that you can get any 3D manifold like that. And this decomposition is useful to compute the partition function now, because that reduces basically our task to compute a general partition function to computing the partition function on one handle body. And that's easy. If you compute the partition function on one handle body, that has been, I think, known in the literature. I'm not sure what to cite here exactly, but it gives the vacuum conformal block on the boundary. And so if we now write our manifold like that, then we can see that the Teichmueller partition function will just be the vacuum block sandwiched with the conformal, with the corresponding operator that represents that crossing transformation, and sandwiched again with the vacuum block. So U of phi is just a unitary representation of this mapping class group element on the Hilbert space, just like this F move, and then there are like other moves, and you can compose them and so on. And so I skipped the inner product, but you can define it so that there's an inner product on the space of conformal blocks. And also you can generalize this to the case with Wilson lines or boundaries and so on, but I'll just restrict to the simple case. So there is an important problem here, of course, is that since the vacuum block appears, the vacuum block, if I would just compute the norm with itself, it would diverge. So if phi, for example, is the trivial, if I don't do any modular transformation before gluing, then obviously I run into trouble. So in general, this inner product may or may not be finite. And it sort of becomes finite if phi is sufficiently complicated. So if you do sufficiently many modular transformations, then it tends to be finite. But we don't currently understand very systematically when it's finite and when it's not. So the sort of conjecture, the very natural conjecture would be that this inner product is finite whenever you consider a hyperbolic three-manifold. Because in this case, there's a semi-classical solution, you can do semi-classical path integrals, and you expect some well-defined answer. And at least in the examples that we considered, this seems to hold up, but we don't have a systematic way of proving something like this. And also, this is a very complicated condition to say the hyperbolic the three-manifold is hyperbolic. So it's very hard to characterize this. Okay, but the advantage of this is that you don't run into some infinity on the way. Like either it's finite or it's not finite. Yes?
I'm a little confused about exactly what kinds of geometries in 3D gravity you're talking about. Were Euclidean or Lorentzian, and they're compact or?
Okay, so here I discussed so it's always Euclidean gravity. We're computing gravity partition functions. Here I discussed the simple case with for closed manifold, so no boundary, no Wilson line. That's the very simplest case. So
they're Euclidean in the language of the TQFT, or they're actually Euclidean in the sense of 3D gravity?
It's Euclidean in the sense of 3D gravity, even though we needed to start with the Lorentzian theory to say what the phase space is. Right? For the phase, I started with SL2R times SL2R, notably not SL2C, Turin times theory or something like that. So I need to start with the Lorentzian theory to say what my phase space is. But once I know my phase space, I do Euclidean quantum gravity.
Example of a Euclidean manifold?
So for example, you can take the complement of the figure 8 knot and things like that. So that sounds a bit
Finite volume?
Finite volume, yes. But we can do that with boundaries. There's no problem with this. It's just more complicated to say, and then you need to introduce more technology. It's not an obstacle. Okay. Well, yeah. You'll see also two examples later on. I mean, one is like the Euclidean wormhole, but you can make it more complete. All right. So now I'll come to sort of the centerpiece of the talk, is namely the relation, the precise relation that we proposed between this Teichmueller TQFT and 3D gravity. And so I already kind of said the argument. It's very simple. If we compute the gravitational path integral, then we need to divide out by the full diffeomorphism group. Whereas in the gauge theory, we only divide out by the sort of identity component of the diffeomorphism group. And so what we propose is that in general, the gravity partition function is related to the square of the Teichmueller TQFT partition function in this way. And I also mentioned this already. So there's a very deep theorem in hyperbolic geometry that ensures you that if you're on a hyperbolic three-manifold, then the mapping class group is always finite. And this has been proven for strictly speaking, the case without Wilson lines, but you can have various asymptotic boundaries. You always get finite mapping class groups. This is called the Sullivan rigidity theorem. And finally, there's, of course, also the important issue that to get the full gravity partition function, we should sum over all different topologies with fixed boundary condition. And we don't have anything useful new to say about the sum, so I won't really mention it very much. So now let me get into some concrete application. And the first application I should discuss is the Euclidean wormhole. So this is sort of the simplest topology in this framework. Euclidean wormhole is just the 3D manifold of this topology. And here we want sigma to be some, say, genus 2 Riemann surface. And it supports an explicit hyperbolic metric, which was first written down, I think, by Malthus and Maus, of this form. So rho parameterizes sort of the throat direction. Rho to 0 is where the wormhole is the thinnest. And then if you go towards the boundaries, this blows up. And so from the TQFT perspective, this is an extremely simple object, because if you have sigma times r, this is sort of the identity. You can glue it somewhere in the manifold, in the 3D manifold. You can cut it open and put this in, and you didn't do anything. Okay, so this represents the identity element in Teichmueller TQFT. And you can view it as a map from the initial Hilbert space, which lives on one boundary, to the final Hilbert space, which lives on the other boundary. And the map is the identity. And so what we can write is that we just need to write it as a resolution of the identity. And for Teichmueller TQFT, we just have one conformal block. So you can think of one conformal block as being the ingoing state, and the other conformal block as being the outgoing state. And you can show conformal blocks are orthogonal, but not naturally orthonormal. So what you need to do is to divide by their norm. Whether you put a bar here or not is kind of up to you. It depends how you choose your relative orientations on both boundaries. And once you work out what the inner product is, what's written there is simply the conformal block expansion of a Liouville correlation function. So now I do get the left moving conformal block and the right moving conformal block. It turns out that these norms are precisely the products of the OZZ structure constants that you need to make a full Liouville correlation function or partition function. So the moduli on both sides of the wormhole can in principle be different, so that's slightly unusual maybe. We can have like Liouville partition function with moduli left and right being different. The mapping class group in this case is simply trivial, so we don't have to worry about it. And so finally, to get the full gravity answer for this topology, what you might also want to do is to sum over different boundary modular transformations. And the ones that you want to sum over are precisely the boundary modular transformation that don't extend into the bulk. And concretely, that means you should only sum over the relative modular transformations. And that leads to this formula that the gravity partition function of the Euclidean wormhole is simply the Liouville correlation function or partition function whole squared, because in gravity we need to square everything. Then we need to sum over the mapping class group the sort of relative mapping class group between those two boundaries. And this sum is really the only thing that entangles left and right. I don't know, I don't remember who asked the question, but someone asked what left and right, why left and right are not completely independent, and the only thing that entangles them is the sum in the end of the day.
On the previous slide, 2 slides ago now, this sum over conformal blocks?
Yes.
That's an integral over the weights?
Yeah, it is a kind of sum integral, yeah. It is an integral over all the internal weights in the conformal block expansion. All right. Okay, so then there's one more example that I would like to discuss, because so far maybe you're not very convinced that this is useful because it's kind of trivial still. So I'd like to consider this topology, which appeared in a recent paper, or plays a role in this paper, that proposed a possible boundary dual CFT interpretation of 3D gravity in terms of an ensemble CFT. And so this is sort of the next to non-trivial wormhole you can consider, which has 4 boundaries. And the simplest topology you can consider is 3 punctured spheres. And then you can consider, you can connect them in this natural way. And these lines here form a tetrahedron in the 3D geometry. And if you now want to compute the 3D gravity partition function of this configuration, it's very simple in this formalism. All you need to do is to cut the picture in half. If you cut the picture in half, you get a 4-punctured, you get like a big sphere, and then there are like 2 smaller spheres cut out, and the lines go exactly like this. And on the other side, you also get the same picture, but it's sort of twisted. So one part will be in the S channel, and the other one will be in the T channel. And so what the partition function here ends up to be is just the inner product of an S-channel conformal block and a T-channel conformal block. And in principle, so all these Wilson lines have some weights associated to it, so you can have 6 different conformal weights in this configuration. Okay, so that means that the inner product is basically just a Verazor fusion kernel, because you need to transform the, say, S-channel conformal block to the T-channel conformal block. And once you have two T-channel conformal blocks, it's very easy to take the inner product. And so you very quickly end up with this statement that the partition function on this four-boundary wormhole is just a bunch of these structure constants, which again come from the inner product, because the inner product is not quite trivial, but it's almost trivial. It's also orthogonal, but not orthonormal. There's some non-trivial measure. So that gives you that, and then you get the Verazor fusion kernel here. So everything here is very explicitly known. And this rho here appears, so the C0 is the these structure constant, some particular normalization that is natural in this context. And this rho is the corresponding two-point function in Liouville. And you can interpret it as being a Plancherel measure on the Verazor group. And sort of a non-trivial test of this formula is that the right-hand side has full tetrahedral symmetry. So this was not obvious from the definition of this crossing kernel, that it will end up having some tetrahedral symmetry, because it only makes reference to a 2D geometry, but this combination does have tetrahedral symmetry. And so this is sort of the maybe simplest non-trivial example that kind of demonstrates the strength of this TQFT way of computing things. But you can just go on and you can compute various crazy things. So Tom asked me, like, what are manifolds we can even compute? So in principle, 3D gravity partition functions are topological invariants of these respective manifolds. And you can consider like knots and complements of knots. So for example, the most famous one that is hyperbolic is the figure 8 knot. Or you can have like Borromean rings and so on, and complement will still be a hyperbolic manifold. So you can go very crazy very quickly and compute these partition functions. It's not clear to me whether they will end up being part of the quantum theory in the end, or whether we want some rules, what we want to include or something. But in principle, this formalism allows you to compute the partition function on all these type of manifolds. And maybe one thing that I haven't emphasized very much, I want to mention also here, is that if you consider sort of semi-classical limit of this whole construction, then you would take the central charge to infinity. And if you take the central charge to infinity, what you expect from the path integral point of view is that you simply compute the volume of these manifolds, because the tree level term is just a hyperbolic volume. And in the cases that we checked, so for example, the figure 8 knot, you can check indeed that this quantum result reduces back to the correct semi-classical result. Okay, so to conclude, I've tried to give a definition of 3D gravity, a precise definition of 3D gravity partition functions in terms of the Teichmueller TQFT. It's computationally very useful, so you can compute all sorts of things that I think were sometimes done already before in the literature, but it was either very laborious or it was sort of by black magic or something. So it's sort of conceptually relatively clear what you should do. And it works at least for all hyperbolic 3 manifolds. If we go to the non-hyperbolic case, there's this problem that the mapping class group might become infinite. We don't know what to do. And so somewhat optimistically, we would hope that this technology helps somehow to settle the question whether 3D gravity makes sense, at least at some level, at the quantum level or not. Well, thank you very much for your attention.
Thank you, Lorenz. Those who are joining us on Zoom, if you want to ask a question, raise your hand and then we'll try to ask your questions.
Thank you. Thank you very much for a nice talk. So I have a question about this large C. So if you consider the 1 over C expansion,
yes.
So do you know if you will match the perturbative expansion that you do in gravity, the semi-classical expansion?
So for the one loop, we could in principle check. We haven't done so, but John Vignier and Maloney computed the one loop. And so I would expect that the 2 prescriptions match. They're like completely different. So it would be very non-trivial to see it, but we haven't done it yet. But I would expect so. For 2 loop, I think nothing has been computed, I think, as far as I know.
Thank you.
Okay, following up to that question, I don't know, maybe you mentioned it and I missed it. Is there a framing anomaly in your TQFT?
Yes, there is. However, in 3D gravity, there's not, because you take the absolute value squared. and so all the phases cancel out. But in just left movers, there is one, except if the center charge is a multiple of 24, then it precisely cancels.
Okay, here's where I think the analytic continuation is making me a bit nervous, because in the case when you are in SU2, and you have the shift by the framing this Coxeter number of 2,
Yep.
which is the level, it is important for matching the one loop corrections between the gravitational side and the Chern-Simons side, at least. So they don't cancel out.
In
They
SU2,
actually-
or you said SL2?
SU2. So
Wha-
when you
what-
interpret
what-
the theory as de Sitter 3.
Okay, I don't know about the sitter, but okay, yeah, maybe we can discuss what precise thing you think is. As far as I know, this is consistent with every computation in the literature that has been done, at least. I'm not aware of any discrepancy.
Do you think there is a flat space version of this story?
No, probably. I mean, you could have asked maybe the slightly simpler question whether there's a positive cosmological constant version of that. And I think the answer is still no. So flat space, I think, is even worse. So the major thing that goes wrong if you try to do positive curvature, cosmological constant, is that you start with an SL2C Chern-Simons theory, and the phase space of that one is just connected. There's just one component. If you try to restrict to the gravity part of it, it's some weird open subset of that phase space, and it's kind of not very good to restrict to that, and it's not clear what the quantization of that should be, and so on, and you fail immediately. And I think for flat space, you run into even worse troubles because there's no like bi-invariant form, and like yeah, and so on. Yeah, so maybe, but there are serious technical problems.
Hi. Is there a generalization to SLNR or HS lambda, these higher spin ones, something like a TODA analog of your statement?
So there I would expect yes, but there are mostly technical questions that need to be addressed. So in principle, yes, you can start with SLNR Chern-Simons theory. There's something called higher Teichmueller TQFT, and there's a particular component again in this modular space that plays sort of the role of Teichmueller space. And I would expect it is quantized in terms of W blocks, but I don't think this has been made precise in the literature. And then for Wn, we are also facing the problem that we don't know what this crossing kernel is. So it's because in the same way as we don't know how to solve TODA theory, and we don't know even the structure constants, there's this problem. So I would expect the answer is yes, but there are technical things that need to be solved.
Sorry, just a quick follow-up. What is the analog of the positivity condition for higher spin theories? Do you have, I mean, what would it translate to restricting to this component? Do you have any?
I mean, one way to define it is that you look at the principal embedding of SL2R into SLNR, and then you sort of take the component with the highest Euler number with respect to this principal embedding. But there's not a very clear geometric point of view with this. But I would expect that Wn blocks should give the quantization. There's a more conceptual point of problem that I don't know how to resolve there, which is what the mapping class group should be in this case. So there's not a higher spin mapping class group that I know of.
So your formula for the wormhole partition function, so you had Z Liouville, that's with the usual Liouville measure, the flat measure on H, as opposed to, okay.
Yep.
Just checking. What, sorry?
I mean,
oh, good. Oh, okay.
It is the thing that leads to a crossing symmetric answer.
Yeah. Okay.
So
Good. Thank you.
There's only one thing that does. Yeah.
So maybe I missed something. We said all hyperbolic manifolds, does this work for the solid torus?
Yes, it does.
So what is the theory in that case, and what happens to these issues with modular invariance?
Okay, good. So this work was just how to compute the partition function on a fixed manifold. So if you do solid torus, this is a particular case of handle body. So what you will get is a vacuum conformal block in the boundary. So that's known for a very long time. And then there's a separate question is what happens if you sum over all the modular images of the vacuum block, and that leads to bad things. So the most bad thing is that you get negative density of states if you only do that. And then there are various proposals how to cure it, maybe include defects. Or, yeah, so this doesn't help at all. This is just in some sense you can view it as just a formalism talk, like how to compute in various manifolds.
Even within this proposal, you're supposed to sum over all the images?
In principle, yes, in the end. But so there is a separate question whether that converges or what it does. Yeah.
Douglas?
You wrote on this slide to compare to Kotler and Jensen.
Yes.
Could you say more about the comparison?
Okay, so from our point of view, Kotler and Jensen is sort of a little bit of a singular case, and I don't exactly know whether it precisely matches or not, because the problem is that, so they consider a torus, so they take a torus times the real line, and the torus is precisely that case where we don't have a hyperbolic metric, so there's no wormhole to start with. So you can work out, you can write down this formula in principle, but the problem is you end up with the Liouville partition function for torus, which is not a completely well-defined thing. And so you have to, so the structure of the answer is the same. That's what I meant by, so that's why I didn't write it's equal to or something. The structure is exactly the same. You have this relative sum over modular transformations. And I think this is the natural generalization to higher genus. And the torus case that they consider is sort of a little bit singular from our point of view. So maybe Christian can say something if he thinks otherwise.
In this case, if I understand right, the prescription you have for dealing with the mapping class group by dividing by some finite number is not going to work, right?
Mapping class group is so if you have a boundary, you only want to look at the mapping class group that is trivial on the boundary. So you look at all the diffeomorphisms that are trivial on the boundary, mapped out by all, the identity diffeomorphs.
Would you need to divide by anything?
No, you don't need. So the mapping class group here is always 1. There's no non-trivial mapping class group.
I mean, there is a discrepancy between the formula that you're writing for a case of torus and what we're writing, because in that case it's infinite and ours it was finite. But the main difference really comes down to the measure over the what's your effective density of states. Whether, and this is why I was asking whether it's a flat measure over H or over the Liouville momentum.
Yeah.
Maybe in defense of what we did, there is a JT limit of 3D gravity, and the answer that we had, you can take the JT limit of it, and in that limit it does match JT.
I mean, if you want, we don't have anything useful to say on it, because this is a singular case from our point of view, and I mean, we can discuss what the Liouville partition function on the genus 1 surface should be, and then maybe we could discuss whether it matches or not, doesn't match. But this explicitly is only claimed for at least genus 2, or if you have sufficiently many punctures.
This may be a good argument in favor of going to 1 loop and 1 over C expansion, because this partition function for genus 2 is known to 1 loop by Giambi-Melloni.
Yeah, so there are definitely cases where you could check against Giambi-Melloni and Yin, which we haven't done, which is something on our to-do list that we should do at some point. Yep.
So what does this imply for the dual CFT? I mean, it looks very much that you can formulate it in terms of Liouville, but it's probably not standard Liouville. So do you have any idea of what you would have to do to describe it?
So it's definitely not Liouville, because, for example, it has a vacuum. I don't know whether there is a use. I don't think personally that there is a single dual CFT. I think more likely something like an ensemble like Scott and collaborators have proposed. Apologies, many of the collaborators are in the audience. But so there's, I think more interestingly is, it's probably hard to say what this ensemble of CFTs is, but there's interesting question whether somehow you can get finite answer by summing over all the different topologies. So in principle, 3D hyperbolic manifolds, they're ordered according to their volume. So they have different volumes. And there's a question, maybe you could sum over all the different hyperbolic 3 manifolds at least. That's the analog of what we do in 2D JT gravity, where we sum also over all the hyperbolic ones. And then there's sort of the sphere and the torus, which are sort of bad because they diverge. And similarly here, there are various manifolds like the 3 sphere, which is bad. And we don't know, maybe we should just throw it out or keep only the hyperbolic ones. So there is a chance, I think, that the sum of a hyperbolic three manifolds might converge, but I'm not sure.
So first a comment, which is that I think this formula we checked at the semi-classical and one loop level in our paper on the simple average, so the one loop does work. But also a question, can you go back to the slide with the four boundaries?
Yep.
So that, I'm trying to, can you say again what exactly the definition of the thing in the ket is? So it's a conformal block of a 4-point function on the sphere, but what are those little loops in it?
Oh, good. So this is supposed to represent still a three-dimensional manifold. So the manifold is a three-ball with two 3-balls punched out, and then there are Wilson lines between those little 3 balls.
So these are not. This is not a Liouville picture. This is a Teichmueller TQFT picture.
Yes. So there is a question: what is the Teichmueller TQFT partition function on that object? And it's maybe not too hard to believe that it gives you the corresponding conformal block in the boundary. But there's this kind of step that I skipped in this discussion.
So this is some complicated linear combination of Liouville conformal blocks for the 4-point function.
So the Teichmueller TQFT partition function on this geometry is supposed to only give you one conformal block in the boundary. Sorry, I feel like we're misunderstanding each other.
Okay, I'll ask you. I'll ask you later.
Okay, so Zoom questions. Alex, can you unmute and ask, please?
Yeah, hi Lorenz. I don't know if you guys can hear me.
We can.
Yes.
Great, thanks for the nice talk. I also have a question about this slide, so it's good that we're on it. I have a comment and a question about non-Gaussianities. So there's another type of non-Gaussianity you can get from modular invariance at genus 3. You basically keep the identity in one channel and you map it to a cross channel, and you get a non-Gaussianity. So you're calling this one the leading. Do you know how the two relate and whether this one is really leading over the other one?
I don't exactly know. Yeah, I don't know. So there's always the problem that there's not a leading, because in 3D there's not a coupling constant, so it's kind of hard to say. But it might, okay, Scott says it's the same, so I'll trust him on that.
Yeah, I think they might be the same. If you take these operators and make them heavy and sum over them, instead of keeping them fixed, you might just land on the genus 3 one.
Scott says it's the same, so.
Okay. Thanks.
Okay, I suggest we thank Lorenz again.
All right, thank you.
And we have a break and reconvene in half an hour.